So now we're going to continue with infinite limits. So what's happening in this scenario is we're approaching a fixed number, right? A is a fixed number. And what's happening is the value of the limit grows without bound. Again, infinity isn't a number. This is describing the behavior of the function, the y values in the function. And they grow without bound as x approaches a number. And again, so the issue is we can't handle this with our standard definition by, say, plugging in or the extension theorem. So in the last case, in limits at infinity, we flipped over the x, right? We said y equals 1 over x. So if x goes to infinity, y would go to 0. Now, we're going to do the same thing here. So f of x is the y-coordinate of the ordered pair, right? Here, our y-coordinate is going to go to plus infinity, grows without bound. So how do we handle it? We'll flip it over. So we have now 1 over y. So now, as y goes to infinity here, 1 over y is going to go to 0. I mean, it's just very, very clever stuff. You'll see this stuff actually in applications and in work you do. You don't have to reinvent the wheel. You build off of what you have. And then we need to know whether the sign. This just says you go to 0. So you could go, if it were going to positive or negative infinity, so growing positively without bound, or negative infinity growing negatively without bound. We need to figure out the sign. So we need to know whether the function is in fact positive for, just to the left, or in this case, just to the right of A. Okay? And again, the issue here is when you see this, an inequality, what do you think? Sign intermediate value property. And they're just all the cases. You can come to A from the left or the right, and you can grow without bound positively, positive infinity, or grow without bound negatively, negative infinity. So again, this is what we're going to talk about, right? So we flip over the y variable, in effect go to 0, and then we have to check the sign intermediate value property. And they're just all the cases. Again, you can come to A and go positive or negative. You can go to A from the other side, from below, and go positive and negative. And you just have all the corresponding cases here. But again, it's the same idea. Here's an example. Usually you're going to grow without bound if you're talking about a rational expression where the denominator is 0, where the function is undefined. So you see we're undefined at 2, and we can go to 2 from the left or the right. So let's examine this. Now, intuitively, and again informally, this is when we were talking about limits originally. Well, how did we handle this? We just made a table, right? We just made a table. So notice 2.1, 2.01, 2.001. We're going to 2 from above, right? 2 plus a little bit, 2 plus a little bit. And we're going to track what happens to the y values. Notice they get very large, in fact, very fast. But we're still, there's still a lot of space between 2.001 and 2. But you can see what's happening. The function's values are growing without bound. And that's what we mean by positive infinity. We're just describing a behavior. Again, there's no point positive infinity. We're just describing a behavior. So again, this is just informally. Again, there's nothing wrong with it. It's always a good idea to have an idea of what's happening before you jump in. I know this is simply a function of one variable. We can graph it. We're trying to introduce broader ideas here in the reasoning process. Okay, so again, that's what positive infinity denotes. But again, I want to emphasize this is not math. It's just intuition. It's an informal analysis. There's nothing wrong to start like this. But again, it's how serious do you want your analysis to be? So let's just apply the definition. Here's the definition. We go to plus infinity as x goes to a number, say 2 from above, provided we have to meet these two criteria, right? So let's consider the first one. So my function is defined here, right? I have the domain. And again, it's a over b. B cannot equal 0. And so what I want to do is, again, I need the function 1 over f of x, but I don't like the limit of that. I like the limit of a function, so I'm just going to call it f tilde x, right? And I'm going to define that to be 1 over f of x. Because, again, I don't know, I prefer this notation. Now notice, I'm just substituting right in here the rule for f of x, right, just from over here. So clearly it's not defined at 2. I mean, if f of x, you can't plug 2 into f of x. If this is 1 over f of x, you can't plug it in there either, right? I mean, it just doesn't make sense. Of course, that corresponds to the infinity value, right? So you can't just plug in there. So again, doing some algebra, just multiply by x minus 2 on the top and x minus 2 on the bottom. This reduces to this case. And the advantage of this is defined at 2, so we can use this rule as our extension. Always the same ideas are coming out. The same ideas are coming out. You only have 2 ways of really looking at the limit. We're either going to plug in, and if you can't plug in, you need an extension. Okay, so now that we have our function, we can start about looking at evaluating the limit. Is the limit point in the domain? No. So can I use point continuity to evaluate the limit? No. Okay, that's fine. It's fine. It just eliminates that possibility. We know we have to use the extension theorem. Okay, so we want to evaluate the limit, and the tool we have is the extension theorem. So here's my function, 1 over the y values in effect, right? And this function is not defined when x is 2. This rule can be, but this function is not. So I can just take the same rule, and now it's defined in fact at 2. So notice that the rules are the same, and we're only looking to the left of 2. To the right of 2, right, for values greater than 2. Our function is a rational function, and it's point continuous when a is 2. Right? We need to check this in order to apply the extension theorem. So what do we have? I mean, if we look at the limit, I defined f tilde to be that function, so I just prefer it like this. By the extension theorem, right, we have f tilde equals to g plus, and again I use g plus because it's 2 plus, right, just for that reason. G plus is continuous, so we can just plug in. We have point continuity, and then we just evaluate the rule, and it's 0. So we did meet the first criteria of the theorem, of the definition. Now we need to check its sign. Is f of x greater than 0? Is it a positive to the right of a? Okay, so we just need an interval to the right of a. Right? There are no zeros there. There's no discontinuities. What's the test point? Just pick a test point. 3, plug it in, the sign, it's positive. Right? We're a rational function. We know the single sign intermediate value applies because there's no zeros here. So we know that f of x is positive for all these x. So we check the second condition, right? We know that since the limit is 0, the function's value are positive to the right of 2. We have then, by definition, that the limit is plus infinity. Again, we're just describing the behavior of the function. Okay? And how does this come up? Well, we can define a vertical asymptote. The line x equals a is called a vertical asymptote if the limit is plus or minus infinity. So let's see how that plays out. Vertical asymptotes typically occur at a discontinuity of the function. Okay, so if you have a rational function in particular, look for the asymptote there, right? So here's the problem. The same function, determine the vertical asymptotes. We already evaluated the limit, so it follows that the line x equals 2 is a vertical asymptote. Now let's look at the picture and see what happens. Okay, so what we have in our picture is, notice the behavior as we go to 2 from below, right? X goes to 2 from below. Notice we're describing the behavior of the function. The values of the function get larger and larger in a negative direction. As x goes to 2 from above, the values of the function get larger and larger in the positive direction. And again, I mean, this is useful behavior. We're analyzing the behavior in the neighborhood of a singularity. So this is the kind of stuff that you look at. And once again, note that the line x equals 2, if you were to back up further and further away, that's what the function looks like. There's no separation here. If you went out, I only went out to 40, go out to 10 billion, then the graph would look just like this line. All the action for this graph is contained down here. Okay? So that's a vertical asymptote. That's what a vertical asymptote is. Now, we're going to use these horizontal and vertical asymptotes later on in the semester when we do graphing. So we'll come back to that. But I didn't want to really introduce these concepts of the limited infinity and the infinite limits. You know, when we got up there, we're talking about limits now and the tools of limits and the techniques of thinking. So I wanted to put this material here, but we'll actually be using it later when we do graphing.